Hi everyone. So today we will be talking about hybridization. So every time I teach hybridization, some of my students say, oh, okay, it must be so difficult to know. But hybridization is actually pretty simple and straightforward. In this lecture, we will be talking about hybridization, but very simply, so it's easy for you to interpret the kind of hybridization present in any kind of compound while forming the chemical bonds. Okay. So the word hybrid or hybridization means mixing, and we know during chemical bond formation we require the mixing of two or more elements. But what happens, the bond formation between the atoms involve electron sharing, electron donation, or electron gaining. So we have learned about this in chemical bonding. Now let's see how the electron sharing takes place through the orbitals. So as we know from the quantum numbers that we have the orbit, which is the principal quantum number, and we have orbitals, which are the subshells or the lower levels or the divisions of the energy levels, and the orbitals are usually sp, d, f, and so on. So we take the example, simple example of hydrogen. So hydrogen has one electron. If we want to write the electronic configuration of hydrogen, this is how this would look. So it has only one electron and it's 1s orbital. Here the principal quantum number is 1, and so it's in the first energy level, and the orbital is s, which has one electron. And we know that each of the electrons can have a maximum of 2 electrons. So here, while forming the hydrogen from two hydrogen elements, what happens is there is a sharing of electron or covalent bond. So both the s orbital of the two hydrogen atoms, they share their electron, and this requires the overlapping or the mixing of two orbitals s. In this case, the s orbitals are overlapping with one another. So this overlapping of the orbitals while forming bond is called hybridization. And we know that the hybridization, one thing you make a common mistake, sometimes my students write down that hybridization happens in electron. No, actually hybridization happens in orbitals while they are forming the bond, and only during the bond formation and not otherwise. So the mixing of the orbitals is hybridization, and there are different kinds of hybridization, and the very common ones which we are always taught are three common hybridization, which I'll be explaining in details. These are sp, sp2, and sp3. So why hybridization is important for us? Because hybridization allows us to know about the bond angles in a compound and also their shapes. So that is why the hybridization are very important. So we would be talking about, first of all, let's talk about the sp3 hybridization. To describe any type of the hybridization, be it sp3, sp2, or sp, we have to take a common example. In this case, I'll be taking the example of carbon, which is a very popular example for hybridization. So carbon, it has 6 electrons. So we write down the electronic configuration, 2s, 2p, 2. So in its outermost energy level, that is 2, it has s and p orbitals, and each of the orbitals has 2 electrons in its configuration. So I'll be writing this portion now. So if I write it down, carbon in its ground state means when it's not forming any kind of bonds. So it's in its ground state, it has in its 2s orbital, it has 2 electrons. In its 2p orbital, we know 2p orbital has 2p subshell has further 3 orbitals, x, y, and z. So the 2 orbitals here are 2px, 2py. So these 2 electrons are present in 2px and 2py. And looking at this, we can understand, okay, since carbon in its outermost energy level has 2 electrons, so carbon must be sharing these two electrons while forming bonds, right? But we know that carbon's valency is not 2, but rather it's 4. And let's see how this 4 comes out from this 2. Okay, so this was when carbon was present in its ground state. Now let's talk about what happens when carbon is present in its excited state, which is when it forms bond. Then this electron, this very electron from the 2s orbital, it jumps up to the 2pz orbital during the excited state of carbon. And so what it becomes now, let's see. So 1s now will have 1 electron because the other one will be jumping up to 2pz, and these were present before, but in addition to it, just one of the electron from 2ps is jumping up to 2pz. So here are the 4 unbonded electron with the help of which carbon forms 4 bonds with the other 4 atoms. And now it makes sense because we know that carbon has 4 valence. The valency of carbon is 4. So we will be taking a short example. So sp3, let's take an example of sp3 is methane, where carbon is sharing 4 covalent bonds with 4 hydrogen atoms. So in here we see that since it's sp3, so carbon would be forming bonds using its 1s and 3p orbitals. Like all 4 of them will be involved here. So here we say that 1, 2, 3, 4. 4 hybrid orbitals has been formed here. 4 hybrid orbitals. Why? Because carbon is using all of its 4 electrons in its outermost shell to form bonds. And so this kind of the orbital involving 1s and 3p orbitals is called 3p hybridization. And while writing that in sp3, in case of methane, we are getting 4 hybrid orbitals, we would say 4 sp3 hybrid orbitals. So every time you write down a hybrid orbital, you can just write, okay, 1 s hybrid orbital and 3p hybrid orbitals. You have to write 1 sp3, 2 sp3, 3 sp3 and 4 sp3. That means each time you say or try to talk about the hybrid orbitals, you have to take the entire name of the hybridization. Okay, this was the example of sp3 hybridization. So just looking at the molecular formula or the structure of it, we can say what should be the bond angle and the shape for sp3 hybridization. So it can be seen that from sp3 hybridization, the bond angle and the shape, these two what we'll be talking about, the shape. Okay, so for sp3 we can say that the compound has a tetrahedral shape and the bond angle would be 109.5 degree. Okay, so from just simple hybridization, we can actually get to know about the bond angle as well as the shape. Okay, so one of the exceptions of sp3 is water. Most of you make confusion when it comes to water, and you are asked to find out the hybridization of water, then some of you get confused. So let's talk about water. In water, hydrogen, the central atom is oxygen. So what happens in water? This is how water looks, right? The central atom is oxygen. And we know that oxygen has 8 electrons, so let us quickly write down the configuration of oxygen. So we can see that in ground state, oxygen has, in its 2s and 2p orbital, oxygen has 1 xpz, okay, now 4 electrons. Okay, so in case of water, we see that oxygen has 6 electrons in its outermost shell, and this is how they are distributed. But as soon as the oxygen wants to form bond, or when the oxygen is excited, then the electron from 2s orbital, it jumps up to 2y, 2py orbital, and that's how it looks. So now oxygen has 2 electrons which can form bond and 2 lone pair electrons. So from this we can see that this actually explains the condition of oxygen in here. With these 2 hybrid orbitals, they are forming water. I mean hydrogen, they are forming covalent bond with hydrogen, and the other 2 orbital are fulfilled because each orbital has a maximum of electron capacity of 2. So these 2 orbitals cannot take part in hybridization because their orbital has maximum number of electrons. So the orbitals left for forming the hybridization are 2s and 2pz. So that's why, because of the presence of 2 fully filled px and py orbitals, oxygen has 2 lone pairs and 2 bond pairs. And in so if we look at it, the bond formation is actually taking place between 1s and 3p orbital. But however, we are not considering the we have to consider the lone pairs when we are talking about hybridization. Although they are not taking part in the reaction, but they are present in the outermost shell, and they are important because for fulfilling the octet. So here for water, in water the oxygen is forming the sp3 hybridization with its 1s and 3p orbitals. Okay, so I hope your concept about sp3 hybridization is clear now. So if it's clear, let's talk about sp2 hybridization. So just like before, we know carbon has 6 electrons, and this is how the electronic configuration looks like. And then when it's in its ground state, it has 2 electrons in its 2s orbital and 2 electrons in its 2px and 2py orbitals. And now, but what happens when the carbon becomes excited to form bond, then one of the electrons from s orbital, it jumps up to the 2pz orbital, and hence now carbon has 4 electrons to form bond in its outermost shell. So what happens in case of sp2 hybridization? Well, in sp2 hybridization, from the name it's obvious that one s orbital and 2p orbitals will be taking part to form the hybridization. So this is what is taking part in the hybridization. So if we consider this, then we can see how many hybrid orbitals are forming here. 1, 2, 3. 3 hybrid orbitals are here, and how many unhybrid orbital? 1 unhybrid orbital. So sp2 hybridization has 3 hybrid orbitals and 1 unhybrid orbital. Okay, now we take an example. A very popular example is ethene. So let us write down the molecular structure of ethene. So here we see that ethene has 2 carbon and 4 hydrogen. So here we know that in carbon, 3 of the central carbon atom will have 3 hybrid orbitals and 1 unhybrid orbitals. And what do we mean by that? And how can we extract information is that here hybrid orbital means actually the sigma bond. The orbitals going to take part in the sigma bond formation, and unhybrid orbitals are the orbitals which form the pi bonds. So here we know that the carbon, every single bond in a double bond and every 2 bonds in a triple bond are pi bonds. So here if there are 4 bonds in the central carbon atom, 3 of them would be sigma bond, sigma, and 1 is pi. And the same goes for this carbon as well. All these are sigma bonds and 1 is pi bond. So when in case of hybridization, we say that okay, sp2 hybridization has 3 hybrid orbitals and 1 unhybrid orbitals. The hybrid orbitals actually indicate the hybridization which takes place between the orbitals through the sigma bond formation, and the unhybrid orbitals through the pi bond formation. So I guess this is pretty clear. Example of sp2 hybridization is the formaldehyde. So first, the first thing we would do every time we are asked to find out the hybridization of a compound is to write down the molecular structure. So for formaldehyde, we would have 2 hydrogen on both sides of the central carbon atom, and it has a double bond in oxygen. So just like before, when we were considering the example of ethene, here carbon will always have 1 pi bond, which means there will always be double bonds when it comes to the sp2 hybridization. So here carbon has 3 sigma and 1 pi bond, and which is evident from this example too. This is 2 sp2 hybridization because it has 3 hybrid orbitals and 1 unhybrid orbital. And sp2 hybrid orbitals always have a trigonal shape. So for sp2, the shape will be trigonal, and trigonals have a bond angle of 120 degree. So yeah, that's all about sp2. Left with sp hybridization. So just like before, carbon is here its electronic configuration. In the ground state, the s has 2 electrons, but in the excited state, the electron jumps up to the 2px or 2pz orbital, and thus giving carbon 4 electrons for sharing. So in here, when we say sp hybridization, that means 1 s and 1 p orbital will be forming the hybridization. Okay, so how many hybrid orbitals we have now here? Because 1 p and 1 s, so 2 hybrid orbitals we have, and we have 2 unhybrid orbitals. So let's take an example of sp hybridization. Another common example for sp hybridization is ethyne. So in ethyne, we see that the carbon, it's forming, so the carbon here, it has sigma bonds, 2 hybrid bonds means 2 sigma bonds, 1 sigma bond here with hydrogen and 1 here with another carbon. So what happens about the 2 other unhybrid bond? Then these 2 unhybrid bonds are actually the pi bonds, 2 pi bonds are here. So the same goes for this carbon. This carbon has 1 sigma bond and 1 sigma bond on either side, and 2 pi bonds with the other carbon. So this is how we get 2 hybrid and 2 unhybrid orbitals in the sp hybridization. And from its structure, we can see that the shape of this molecule is linear, that this carbon has 2 sigma bond on either side and 2 pi bonds on with nitrogen. So thus the 2 hybrid and 2 unhybrid orbitals can be seen. So this is sp hybridization. Now let me give you a few home tasks. Try yourself and try to find out the hybridization of these compounds, and please get back to me. From hybridization, we saw that the hybridization actually is helping us to guess the shape of different compounds. So the molecular geometry, the shape of different compounds means the molecular geometry. So because of the molecular geometry is observed only because of the bonding and the lone pair electrons around the central atom. So from that, we seen that sp gives a linear shape, sp2 hybrid molecules give trigonal shape, and sp3 gives the tetrahedral shape. And now from studying the hybridization, the scientists found there is something that's called the VSEPR, that is the valence shell electron pair repulsion theory. So from their observation, we see that we write the carbon dioxide formula as two lone pairs and 2 bond pairs, and here the central carbon atom has no lone pairs, it has 4 bonds on in total. But when writing the formula of oxygen, the molecular structure of oxygen, we see we are writing it as a bent structure instead of a linear structure. This is the right form and this is the incorrect form. And now the question is why? the answer lies in this theory. So from hybridization, the scientists thought that since the electrons, they are negatively charged particles, so we know that negative charges will always repel the same charges. So the negative electrons will be repelling one another. Like when it is arranged around the central atom, we see that the bonding electron pairs have formed bond. That's something else. But what about the lone pair electrons, how they are arranged? So depending on the repulsion of the lone and the bond pairs, the central molecule develops such a geometry, and that can be explained by the valence shell electron repulsion theory. In short, it's called Vesper theory. So what does the Vesper theory states? Well, it states that since the central atom has, in case of oxygen, it's a very good example. Why? Because oxygen has two electrons, two lone pair electrons and two bond pair electrons, right? So in this case, the lone pair electrons and the bond pair electrons will be arranged as far from each other as possible, so that the repulsion between them is least. So in order to have the least repulsion, we have to increase the distance. That's what the theory says. So and it has been found that the repulsion between lone pair and lone pair is higher than the repulsion between lone pair and bond pair, and which is also a little bit higher than the bond pair and bond pair. So in short, we can say that the lone pair and the lone pair has the greatest repulsion possible, and the lone pair and the bond pair has a moderate repulsion between them, and the least repulsion is observed between the bonded pairs of electrons. And hence, from this is very evident from the structure of water molecule with the central oxygen atom. So here we see, according to this is how the water molecule should look like. Why? Because the repulsion between the bond pair is least, and that's how we see that the bond here, they are distant in such a way, they are not distant, a very great distance. They have a minimal distance because the repulsion is least. And then the moderate repulsion takes place between lone pair and bond pair. This is a lone pair and this is a bond pair, so they should be well far apart from each other so that the repulsion is least, and the greatest repulsion takes place between the lone pairs, so they should be fixed in the farthest possible distance from one another, so the repulsion force is least. So this is why the structure of water is bent, but the structure of carbon dioxide, it is straight. And on the other hand, we take the example of, also let's take the example of ammonia. And how do we write the structure of ammonia? Well, most of us, we write the structure of ammonia like this, but it has a lone pair electron here, right? So according to Vesper, the structure of ammonia should be like this. Why? Because the bond pair electrons have least, they do have repulsion, but it is lesser than that of the bond pair and lone pair electrons. So the distance here is greater than that of here. So hope your idea is clear about Vesper.